Okay, we're recording.
Okay, welcome everybody to another installment of the New England Dynamics and Number Theory seminar. Today's speaker is Nicolas Chevallier from Université de Haute-Alsace. He will be speaking on minimal vectors in C2 and best constant for Dirichlet's theorem over C.
Thanks to the organizer for the invitation to talk about minimal vectors and about the best constant for Dirichlet theorem. I will start with some history, then with some easy results about minimal vectors, then with about less easy results about minimal vectors with some proof, and then about the best constant for Dirichlet theorem. And depending on time, I will talk about continued fraction associated with minimal vectors. So let us start with some history. Minimal vectors go back to Voronoi, and here I adopt the presentation of Burman of Voronoi algorithm. So you have a discrete subset E in the positive quadrant of RD, and you suppose that the positive quadrant of RD is equipped with the usual order, this order here, and you say that a point in the discrete subset E is minimal if it is a minimal point in the ordered set E. Now, what is Voronoi algorithm? I still follow the presentation of Burman. Just a notation before, if you have a point y in Rd, the set hi of y is the set of x in the positive quadrant with such that the ith coordinate of x is greater than the ith coordinate of y, and all the other coordinate of x are smaller than the coordinate of y, with at least one strict inequality. So if we have t equals to 2 and a point y0, we have two sets, h1 here and h2 here. Now, what is Voronoi algorithm? In fact, it is a geometric object, the following one, still by Burman. An I chain in E is a sequence of minimal points in E, yn, such that yn plus 1 is the minimal point in the intersection of E and hi of yn with xi minimal, smallest as possible. So just an example. Here we have a set E with a blue point, and we have y0, which is a minimal point, which means that this rectangle contains no point of E, and we take a next point in the chain, which is y1. The rectangle here contains no point of E. This is a minimal point, and it is a minimal point with the smallest second coordinate, because we look at a two chain here, and so on. So there is the two chain here, y0, y1, y2, y3, and so on. Voronoi use this algorithm to find fundamental units in the ring of integers of a cubic extension of Q. He used the previous algorithm with the set E defined as follow, just this set where sigma 1, sigma 2, and sigma 3 are the three embedding of the cubic field in R, in fact, because it must be a real extension here for this algorithm. Voronoi algorithm was extended by Burman to some quartic, quintic, and sextic fields in order to find some fundamental units in the ring of integers of these fields. If you apply Voronoi algorithm in the simple case of the set E given here, you take theta in R and you look at all the pairs is here, defined like here, and you look at the minimal point and the two chain, for instance, and you get the usual continued fraction algorithm applied to theta. You can also look at Voronoi algorithm applied to lattice in R2. And if you look at what you obtain looking at all lattices in R2 and the Voronoi algorithm applied to all these lattices, in fact, you obtain the natural extension of the usual continued fraction algorithm. So the natural extension of the Gauss map.
Excuse me, Nicolas. So can you clarify what is the goal of the algorithm? What is it computing?
For Voronoi or for me?
For Voronoi.
For Voronoi, the goal of the algorithm was to compute the fundamental unit of the ring of integers of some cubic field.
Yeah, true. But now you say that you apply Voronoj's algorithm to continued fractions. So what is the outcome? What is it computing?
Yes, I say you see for this item, this one. I don't know what Voronoi says about it, but if you just take this set, the set E defined by the absolute value of P minus Q theta and
yes.
absolute value of Q, you take this set, and if you look at the minimal vectors in this set, and for instance, if you look at the second coordinate here, you obtain exactly the denominators of the convergent of theta, just looking at this set.
Can you please, Nicolas, can you please go back just to the slide where you made the drawing of the sequence yn?
Yes, here?
Yes, so here, okay, so what would it be here, y1?
So you start with one minimal vectors, for instance, y0 here, minimal vectors in the set E, because it is minimal because there is no point smaller than this one for the natural order of the positive quadrant. The rectangle here is empty. And now you look at the point of E in the region H2 of Y0, and you take the minimal vector with the smallest second coordinate in this region, and it is Y1.
So here you specify.
And you continue.
It's for 2. You're doing it for 2.
Yeah, yes, I do it for 2 here, not for 1.
You can do the algorithm for 2. You can do it for 1.
In the following, I will always do it for 2. You see, you look at the denominator increase.
But is it the same as the boundary of the convex hull of E?
I don't think, no, I don't think so. No, it is not the same. It is not the same. Yes, you can look at the line polyhedron. It may be the convex hull of all this point or something like that. I don't think it's
so in the case of the continued fraction, okay, you will be starting. Where are the QNs now? Yes, you will be computing.
The QNs, these are the second coordinate of the vectors, of the minimal vectors.
Good.
So now I go to the complex case. Just the definition of a Gauss lattice. It is a subset of a C vector space of finite dimension, which is a submodule over the Gaussian integers, and which is discrete and which generates the vector space V. And now we can say that a vector in lambda is minimal if we look at the modulus of its coordinate in C2, for instance, if the corresponding vector with the image in E is minimal. We can also define directly what is a minimal vector in lambda. I do it in the next slide. So just, we need just a notation. If you have a vector u in C2, you can define the cylinder Cu, which is just the point in C2, such that the modulus of the coordinate of the point x are smaller than the modulus of the coordinate of u, smaller or equal. And now we can say that a point u is a minimal vector in a lattice lambda, in a Gauss lattice lambda, if for every non-zero v in lambda, if v is in the cylinder Cu, then it means that the absolute value of the first coordinate of v is equal to the modulus, sorry, of the first coordinate of u, and the same for the second coordinate. And what will be important for us will be pair of consecutive minimal vectors. These are defined obviously, and it is just minimal vectors such that the first coordinate of the second coordinate of u, the modulus, is strictly smaller than the modulus of the second coordinate of v, and there are no minimal vector in lambda such that the second coordinate lie between the two second coordinates of u and v. So these are the minimal vectors, and these are important for our talk. Now I will explain a few easy properties of consecutive minimal vectors and of minimal vectors. So first thing, if you have two minimal vectors in a lattice in C2, then you have either that the modulus of the coordinate are equal, or that if one of the coordinate of u is, the modulus is greater than the corresponding coordinate of v, then for the other coordinate, it is in the other direction. The inequality is in the other direction, like that. You see, this is clear. Another lemma which is clear is that if you have a lattice in Gauss lattice in C2, and if you have a minimal vector such that the first coordinate is not 0, then you can find a minimal vector v that u and v are consecutive. Because if you look at u and you consider the infinite cylinder defined by the first coordinate of u, in fact, the interior of this infinite cylinder of point such that the first coordinate is smaller than the modulus of u1, so the green region here, this green region must contain a point of the lattice. Because, for instance, you can use the Minkowski convex body theorem. This region has an infinite volume and is convex, symmetric. And so you have some point of lambda in here in the green region, and you can then take a point of lambda which has a minimal second coordinate. The modulus of the second coordinate is minimal, and if there are many such vectors, you take a vector such that among these vectors, such that the first coordinate is minimal among them. And this gives you a minimal vectors in the green region. And it will be consecutive because the second coordinate has been chosen minimal. So you have two consecutive minimal vectors. This is easy. Another thing which is easy is that we can recognize with some cylinder when two minimal vectors are consecutive. We just need this notation. If you have two vectors in C2, u and v, you can define the cylinder CUV, which is the set of x1, x2 in C2, such that the first coordinate the modulus of the first coordinate of x is smaller than the modulus of the first coordinate of u, and the modulus of the second coordinate of x is smaller than the modulus of the second coordinate of v. Now, it is easy to prove the following thing. Two vectors u and v are consecutive minimal two minimal vectors u and v are consecutive if and only if the modulus of u2 is smaller than the modulus of v2, and 0 is the only vector of lambda in the interior of the cylinder CUV. This lemma is easy because if u and v are not consecutive, by definition, there will be some minimal vector w with the second coordinate between the coordinate of u and v, and this vector w will be in the interior of CUV. And conversely, if you have one vector in this interior, then the cylinder defined by this vector w, it must contain a minimal vector, this cylinder, and this minimal vector will contradict the definition of the fact of that u and v are consecutive. So it is an easy lemma. We will use it many times. When you have a lattice in C2, you can look at all the minimal vectors. You can look at the sequence of all minimal vectors, which means the following thing. This must be a sequence of minimal vector indexed over an interval in Z. And when you take two consecutive terms of this sequence, they must be consecutive minimal vectors. And for all minimal vectors in lambda, you must have some integer n in D such that the modulus of the coordinate of x are equal to the modulus of the coordinate of the minimal vector xn. And as we explained before, in that case, if we call Rn of lambda the modulus of the first coordinate of the minimal vector xn, and Qn the modulus of the second coordinate, this must increase, the second coordinate must increase, and the first coordinate must decrease. We just must be careful of the meaning of sequence of all minimal vectors because of the following thing. First, if you have a minimal vector in the lattice, then minus this vector is obviously also a minimal vector, and you can also multiply this vector by I. It will give you another minimal vector. So when you have one minimal vector, you have four minimal vectors at the same time. The multiplication by I gives you the four minimal vectors, but it can happen some strange thing, which is just written here. It can happen that you have two linearly independent minimal vectors in a lattice such that the modulus of the coordinate are equal. So in fact, when you look at the sequence of all minimal vectors, you can skip some minimal vectors, but what is important in minimal vectors are not exactly the minimal vectors themselves, but more the modulus of their coordinate. So now, one easy thing is the relation between minimal vector and best approximation. I just recall one definition. When you have
sorry, Nicolas, could I ask
yes,
naive question about that last thing you said? I just was a little confused because I thought we are only in the positive quadrant. So if you multiply by I.
No. In fact, yes, it is little bit maybe my presentation, because when I define following minimal vectors following Burman, I look only at a point in the positive quadrant, you see. And if you have a lattice lambda, the first thing you do is that you take all the modulus of the coordinate in order to get a subset of the positive quadrant. But after I just say that we defined minimal vectors without the positive quadrant, looking at the cylinder, it is the same thing, in fact. Because saying that there is no vector in the cylinder defined by a vector u except vector that have exactly the same modulus, the coordinate have the same modulus, means that the corresponding point in the positive quadrant is minimal.
I understand it now. Yeah.
Yes.
I get it. Thank you.
Excuse me. And one question also, Naif, this sequence Rn and Qn.
Yes.
If you have the largest decreasing sequence and increasing sequence that does this, it will be the sequence of minimal vectors?
Largest, I don't...
I mean the richest, that you don't skip.
If we don't skip any vectors, I don't think so. No, I don't think so, because when you see, if you project the lattice on one axis, then it will be a dense subset of the axis, and the number Rn or Qn, this is a discrete subset of R.
Okay.
You see?
Yes. Okay.
Yes.
So it doesn't work like this. Okay. But so this Qn is increasing. This is like in the, this is.
Yes,
okay.
because, yes, it is increasing because we say that xn and xn plus 1 are consecutive. And in the definition, we put that the second coordinate of the second vector of a pair of consecutive minimal vectors, the second vector must have some, the second coordinate must be larger than the second coordinate of the first vector. So this is why this is...
And then that the other one is decreasing is from the fact that it's minimal and...
Yes. Okay. The inequality must be on the other direction for the other coordinate. And here we have only two coordinates. It is easy because of this. Now if you have a complex number z in C, and you say that a pair of Gaussian integer PQ is the best approximation vector of Z, if Q is not 0, and if for all pair AB of Gaussian integer, if the modulus of B is between 0 and the modulus of Q, then the approximation given by the pair AB must be less good than the approximation given by PQ with a strict inequality here. And if you take B of the same modulus than Q, then the inequality must be large, because it can happen that for some other pair, you have the same value. And in fact, PQ will be still a best approximation vector. Now, there is a connection between best approximation vector and minimal vector, because if you take a complex number Z and you look at the lattice lambda Z here, these are the pairs P minus QZ Q with PQ Gaussian integers. This is a Gauss lattice here. And the minimal, the vector P minus QZ Q with Q not zero, is minimal in lambda z if and only if PQ is the best approximation vector of Z. And this is very easy to see that. Just a picture. You have a vector here, P minus QZQ, and if you suppose that this vector is minimal, this means that the cylinder defined by this vector, on the picture, this is just this rectangle, then this rectangle, this cylinder must not contain some vector of lambda z. So if you take a vector of lambda z, which defined by A and B, and if B is smaller than Q, this point is not in this cylinder, which means that the horizontal distance here must be greater than this horizontal distance here, which means this inequality. And just we look and we also see that this must also be true. So, conversely, it is also clear. So there is a correspondence between minimal vectors in lambda z and best approximation vectors. With this, we can look at the Dirichlet constant for the approximation of complex numbers. Just a definition of a constant. If you take a complex number C, and you can say that d of z is the infimum of all the positive constants C, such that for all real number Q greater than 1, there exists a pair PQ of Gaussian integer such that Q is between 0 and the modulus of Q is between 0 and capital Q here, and the approximation given by PQ is smaller than C over Q. So for each complex number, we have a constant d of z, and the best Dirichlet constant in the theorem of Dirichlet is just just before to explain this constant d of z can be computed with the sequence of best approximation vector of z. This is just given by this soup here. You take the, I assume that these are the sequence of all best approximation vectors given by increasing Q here. And you just have to compute this product. This is the first coordinate of the minimal vector corresponding to Pn, Qn. And this is the second coordinate of the next minimal vectors, the modulus of the second coordinate of the next minimal vectors. It is quite standard, I think. And now you can, we are looking for the soup over all complex number z of this constant d of z. We can look at the same thing, but with all the lattices in C2 and define so the constant associated with a unimodular lattice in C2. A unimodular lattice in C2 is just a lattice such that you have a basis of this lattice, and the complex determinant of this lattice is 1, I minus 1 or minus I. It's a unimodular lattice in C2. And then you can, instead of computing this soup, you can compute this soup where Rn and Qn are given by the sequence of all minimal vectors. And then you can compute the soup over all lattice lambda, all unimodular lattice. And this you can formulate even directly. you can compute the sup of all the product modulus of U1 and times modulus of V2 for all pair of consecutive minimal vectors in all unimodular lattice in C2. And obviously, this sup here will be larger than this sup here. It is this one we want, but this one is larger. And we will try to compute this sup. Now,
excuse me, Nicolas. So for the second problem, you don't want module over Gaussian integers anymore, right? Is that correct?
May you repeat?
So this lambda, unimodular lattice lambda, is not a module over the Gaussian integers.
It must be over Gaussian integer.
It's still a module over Z over
yeah. In all my talk, only Gaussian integers. No other ring in C.
I see. Okay. And another question is, in this definition of D of Z and D of lambda, you have supremum over N.
Yes.
So will this supremum sometimes?
Lim sup will also work if you want.
Okay. Is it the same? That's my question.
It is the same.
So probably
it will be the same. Yes.
Maybe you need some irrationality assumption over of Z.
For what will be the same is if you find this for one lattice lambda, I don't know, but the sup over all it will be the same.
Yeah. This I understand. Yeah, but for one lattice you don't know.
For one. I don't know. I think it may depend on the lattice.
I see. So
for all lattices.
So in other words, if in the beginning of the slide you say you define it the infimum of C such that for all Q something happens. So I think usually when people try to do this, they write for all large enough Q something happens.
Yes. But
which is related to my previous question.
Yes. But it is almost the same at the end.
But at the end, it will be the same. I understand. Okay.
Yes.
Okay.
So now we are.
You have three sup. The first two are equal.
We have so we have this sup here give you D of Z, and then what we are looking for is this sup, because
yes,
this
I understand, but yes, but is this sup the same as sup for lambda? Yes, this one.
No, it is not clear. The only thing which is clear is that the sup for lambda is larger than this one. But in fact, they are equal, in fact.
Okay.
At the end. But the only thing we know at first sight is that the sup here is larger than the sups than this one. Okay?
Yes.
And now the first not easy, not difficult, but not easy result is the following. If you have two consecutive vectors in a lattice over Gaussian integers in C2, then the sublattice generated by U and V is of index 1 or 2. This means that if you look at the quotient of lambda over this sublattice, there is 1 point or 2 points in the quotient. And if this is of index 1, obviously this is lambda, this lattice, and if it's of index 2, this lattice is not lambda, but you can recover lambda with UV only. These lambda are given by the linear combination with and H, both Gaussian integer, or both in the set G here. And the set G here is the multiple of 1 over 1 plus I that are not Gaussian integers. If you think of the real case, it is just the set of half integers which are not integers. And if you take all the point with integer coordinate or half integer coordinate, both half integers coordinate in R2, this is a lattice. And this is here, we have the same thing. In the case of R, if we take lattice in R, and if we take consecutive minimal vectors, then we have only index 1 pair of consecutive minimal vectors. I just explained this fact before going into the proof of this theorem. I will explain most of the proof of this theorem. And in the real case, it is easy because if you have U and V, two minimal vectors, consecutive minimal vectors, you know that the cylinder defined by U and V must be empty. There must be no lattice point except 0 in the interior of the cylinder C of UV. Now, if the lattice generated by U and V is not lambda, this means that the parallelogram defined by U and V must contain a lattice point. But this lattice point cannot be in C of UV. So if you have a lattice point inside in the parallelogram here, it must be in the red triangle here. And if it is in the red triangle here, you can translate the picture with minus U plus V. And if you translate with minus U plus V, the point W will be here inside the cylinder C of UV. So it is impossible that there is another vector in this parallelogram. And this means that U and V are of index 1, or we can say are primitive in the lattice. So in the real case, it is clear that only index 1 consecutive minimal vectors are possible. In the complex situation with Gaussian integers, it is not so easy. So we call L the lattice generated by U and V. And since U and V are consecutive minimal vectors, we know that the second coordinate of U is smaller than the second coordinate of V, and the reverse inequality for the first coordinate. So if we compute the determinant of the lattice L, we find this, and this is smaller than 2 times these terms, so smaller than that. Now, the real determinant of the lattice L, the absolute value of this determinant, it's just the square of the modulus of the complex determinant. So this is smaller than 4 times this product. But this product, it is the volume of the cylinder C of UV up to the factor pi to the power 2 here. So this is equal. And now we say before that since U and V are consecutive minimal vectors, the interior of the convex body CUV cannot contain lattice point. So we can apply Minkowski convex body theorem, and we get that this volume is smaller to 2 to the 4, because the dimension of the real dimensions of the space is 4, so 16 times the determinant of the lattice lambda. This gives that the ratio of the determinant of the real determinant of L and the real determinant of lambda is just smaller than 64 over pi square, which is a little bit more than 6. And now, since this ratio is the square of the ratio of the modulus of the complex determinant, and the ratio of this complex determinant must be a Gaussian integer, because you can compute this ratio just by computing the determinant of a basis of L in a basis of lambda, and it must be a Gaussian integer. So this means that this ratio must be the sum of 2 squares. So it cannot be, it must be less than 6, but it cannot be 3 and it cannot be 6. So this ratio must be 1, 2, 4, or 5. And what we want to prove is that 4 or 5 is impossible. I just explained not entirely this thing, but a part of this thing. Since the Gaussian integer is a Euclidean ring, it means that we can find a basis capital U, capital V of lambda and Gaussian integers A, B, and C such that small u, small v have the following shape here. Next, u is a minimal vector. This means that u cannot be the multiple of some other vector, which implies that A must be a unit. And you can change capital U, and so you can suppose that A equals to 2. Now you can compute the determinant of small u, small v in the basis capital U, capital V, and the absolute, the modulus of this determinant to the power 2 is just C modulus to the power 2, and it must be 1, 2, 4, or 5, and we want to explain that it is not 4 or 5. I just explained that it is not 4. If it is 4, this means that C must be 2, 2i, minus 2, or minus 2i, and you can still use the multiplication by I, and you can suppose that C is 2. And if C is 2, we want to find a contradiction. So we want to find a linear combination of capital U and capital V, such that this linear combination with Gaussian integer coefficient is in the interior of the cylinder defined by C, by U and V. And we just look at a linear combination like that. W is V plus G times U. And we compute it with small u and small v using the system here that we can solve. And we find this. And so we have a linear combination of the minimal vector u and v. And here we have the coefficient of u. And if we want that this vector is in this cylinder, what we want to, we want that the coefficient here is as small as possible. So we are choosing G such that this coefficient is as small as possible. We can do this like that. You look at the ratio B over C, and there is a Gaussian integer G, which is at a distance less than 1 over square root of 2 from this ratio. Then this Gaussian integer has a modulus smaller than square root of 2, because we just multiply by C equal to 2. And this means that this modulus is 1, is 0, 1, or square root of 2. And we want to see that this possibility all leads to a contradiction. First, if this is 0, This means that W is just 1 over C times V, but this is not possible because V is a minimal vector, because W will be 1/2 of V, and this is not possible. If it is 1, the modulus, then you look at what you obtain. You obtain W is 1/2 times a complex number of modulus 1 times U plus 1/2 of V. This vector G minus B times U is still in the cylinder CUV. And so you have the middle of 2 points of this cylinder, but one of the points is on the lateral side and the other point is on the upper side, and this means that the middle is in the interior, so this is impossible. I skip the last case. It is a little bit more difficult, but elementary as the previous case. And for the case of modulus of C square equal 5, it is the same kind of argument. Everything is elementary. Now, before going to the main theorem, I just explain, I must hurry. So I skip this. It was just a real case. It was obvious. I skip this. The main theorem is the following one. You have what we want to recognize when two vectors are consecutive minimal vectors in a lattice. And we know that when they are consecutive minimal vectors in a lattice, either they are consecutive minimal vectors of index 1 or of index 2. And we also know then when they are consecutive minimal vectors of, in any case, there must be, there are some conditions on the coordinate. That is, the second coordinate of V is larger than the second coordinate of U, even strict inequality. And here, the first coordinate of U is larger than the first coordinate of V. We know that must be true. And what we want is that in the first case, when U and V are of index 1, we want that the cylinder C of UV contains no point, no non-zero point in its interior of this lattice. This means that we want that no point of this set is here, and we want to check this with finitely many conditions, and these are given here. To check that no point of this lattice is in the interior of this cylinder, it is enough to check that all the linear combination G times U plus H times V are not in the interior of the cylinder for all the non-zero G H Gaussian integer with modulus smaller than square root of 2. This means that we have very few things to check, because there are modulus of G can be only 1 of square root of 2. G can be only 1 or I or minus 1 or minus I, or 1 plus I and the multiplication of this complex number by I, minus 1 and minus I. This means that there are very few pair GH which satisfies this inequality. And we have just to check that these vectors are not here. And in the second case, it is even simpler. What we want is that there are no vector of the lattice here, we defined before, which are in this cylinder. And we have only to check that these linear combinations are not in the interior of the cylinder when G and H are multiple of 1 over 1 plus I, multiple by I of this vector. So very few conditions to check here. Maybe I sketch the proof just to show one thing important, is that the following thing. When we have two vectors, and like before, if the first coordinate of u is larger than the first coordinate of v, then it means that the first coordinate of u of v we can it is of the following shape: u1 times w1. W1 is just a quotient of w of v1 over u1, and the same for the second coordinate of u. It is v2 times w2 for some complex number w2 smaller than 1, the modulus of which is smaller than 1. We will use this norm. This is a norm, the subnorm, which is just defined with the first coordinate of u and the second coordinate of v. It means that when we compute the norm uv of some vector, and if we want that the vector is outside, is not in the interior of the cylinder C of uv, it means that this norm is larger than 1. And next, just this small computation show an important thing. If we look at the norm of GU minus HV, then by definition, it is just the maximum of these two ratios. And we can simplify with U1 here and with V2 here, and we can factor H here, and we can factor G in the second ratio, and we find this quantity, which is interesting, geometric, interesting quantity, because here we have the modulus of H times the distance between W1, the point W1, and the ratio G over H, and here it is the distance between W2 and the inverse ratio here. And we see that it depends only on W1 and W2. It does not depend on U1 and V2, only W1 and W2. This is important thing. We can, in fact, use some symmetries to reduce ourselves to the case where W1 is in this sector, the sector of point in the unit disk with argument between 0 and p over 5. This is because we can use the symmetries which are the multiplication by I and also the conjugation of complex numbers. And now, if we suppose that W1 is in C here, in this sector, then if we try some special pair of Gaussian integer, GH, these two pairs, we can see that this sector is inside the circle of center 1 and of radius 1. And this means, using that we want that this is larger than 1, since this will be smaller than 1, this must be larger than 1. This second term must be larger than 1. And this implies, so if we use these two pairs, this implies that W2 is in the region D, defined here. This is the set of complex number of modulus smaller than 1, and the distance of which to 1 is larger than 1, and the distance to 1 minus I is larger than 1. Then, if you use elementary geometry, you see that when modulus of G or modulus of H are larger than 6, then this norm is larger than 1. So these points are not important. And so we are left with only finitely many pair of Gaussian integer, and you can use a computer to finish the proof. We can finish the proof with the computer, because we can compute for each of these pair and h, we can compute the distance from G over H to C and the distance from H over G to D. This is what we can do. And what we find, the important thing is just, I will say it here, is the following thing. We can completely describe the set of W1 and W2 that we can, which verifies the theorem. In the first case, for instance, these are given by the picture. In the theorem, I just say that there are finitely many G and H with which are the Gaussian integer with modulus smaller than square root of 2. In fact, if we suppose that W1 is in C, we have only 5 pair of GH to consider, and the 5 pair of GH to consider are 1, 1. We already talk about this pair. The pair also 1 minus I here, and these are the 2 pairs which define D, and there are 3 other pairs. I just explained what happens for this first pair here. If we take G equals to 1 and H equals to 1 plus I, then we look at these as this thing. And we take first the second coordinate. If the distance of W2 to this point is smaller than 1 over 1, is smaller than 1. In fact, it means that W2 is in the disk defined by the blue circle here. So if W2 is in this region here, in the blue disk and also in D, then the other inequality here must be satisfied. This means that the distance from W1 to G over H must be larger than 1 over modulus of H, so 1 over square root of 2. This means that W1 must be at a distance larger than 1 over square root of 2 from this point. And so it must be not in the circle defined, in the disk defined by this blue circle. So it must be here. If W2 is here, W1 must be here, and you have some other condition here. If W2 is between these 2 circles, then W1 must be outside the red circle here, and so on. If W2 is in the green circle, then W1 must be in the small region under the 2 circle green, and the green and the red region. So we can describe everything. And it is the important thing to prove this theorem. This sup we want to compute is square root of 2 over 3 minus square root of 3. When we try to compute this sup over all pair of consecutive minimal vectors in unimodular lattice. And a consequence of this theorem is that the best Dirichlet constant for the approximation of a complex number is also square root of 2 minus over 3 minus square root of 3. This is the same constant, in fact. I just say a few, very few words about the proof. The proof go like that. You take 2 minimal vectors and you use as before W1 and W2, and you compute the determinant. This determinant must be 1 or square root of 2, according that if U and V are of index 1 or index 2. And if you compute this, you see that this is this product. which means that, for instance, in the case of index 1, we just have to find the supremum of this quantity when W1 and W2, they must satisfy the condition of the previous theorem we have just explained before. So we must just compute the minimum of the function here, modulus of 1 minus W1 times W2 for all the possible W1, W2, but these are given by the previous theorem, and we can still use symmetries. And so we are reduced to study this simple function over a not so complicated set, because the set is given by the circle I just explained before. And so you have just to look at the many case and to look at try to compute on each part of the set what is the minimum. And I can sense that the minimum is given when you take W2 here and W1 here. This is the minimum here. And so we have proved the theorem with this. And maybe I just show a next picture just to see. We can, with consecutive minimal vectors, we can construct a continued fraction algorithm, we can say, because when you have two consecutive minimal vectors, it is easy to compute the next one. And as before, the important parameters are the ratio V1 over U1 and U2 over V2. And there are two cases. When you compute the next minimal vectors, it is easy. You just have to look at a finite set and choose a right point in here. And what is important is that when you have the next minimal vectors, you have also the next pair of minimal vectors. So if you have UV, a pair of minimal vectors, and you find V prime, the next one, and the next pair is just V prime. And you can compute the new W prime 1, W prime 2, and this is easy to compute. These are just these two numbers, and these are when U1 and U and V are of index 1. When U and V are of index 2, so in that case, it is the formula are a little bit more complicated, but this is easy to compute, to prove, and we can prove this. And we can iterate this map, and I just show the iteration of this map. Here, there is more than 100,000 iterate of one point, and the point, we only look at the W1 and W2, not U1 and V2, just W1, W2, which are the important parameters. And the drawing is only done when W1 is in C here. And we see the previous constraint we have shown in some picture before, is that when W2 is in the blue region here, W1 cannot be in the blue circle here. And if we want to see the thing more clearly, we can remove the orange point. For the orange point, there are no constraints here. They can be anywhere. So there are too many orange points to see something. We can remove them. And if we remove them, we see this. These are the iterate of the point. And we can look at the pair. Sometimes the pair of minimal vectors fall in the case of index 2. And if we fall in the case of index 2, we find this picture. And this picture means that when W1 is here, W2 is here, anywhere here. When W1 is anywhere here, W2 is in anywhere here, and so on. We have 4 pieces. These are the iterates. And I think I finished. Thank you for your attention.
Well, let's thank our speaker. And are there any questions or comments?
So can I ask something which just came to mind? So you also mentioned that the set of numbers for which the constant is smaller has measure 0. Right? You had
Yes,
this,
yes. I also mentioned in my paper. I also mentioned that. Yes.
Yes, I saw that. And I guess if you want to prove it, so it's a dynamics and number theory seminar. So this is a part which is related to dynamics. Am I right? Is it?
Yes. This is the part related to dynamic. Yes, but I think the argument are maybe not completely standard, but more standard maybe. Yes. Yes, it is dynamic after. Yes.
Okay, but in other words, if you so you're saying that the constant is strictly smaller. If you can say something about the orbit of the lattice associated with this number, and what is this property? What does this orbit do?
Yes, in fact, when you see, I just come back with maybe this picture. When you take W1, W2 here, and W1 here, you can look at the pair UV associated with these two numbers, and you obtain a lattice and generated by U and V. And if you look at the cylinder defined by U and V, this cylinder has some volume and contains no point of the lattice defined by U and V. Mm-hmm. So if you take some lattices which is close, which from the lattices defined by U and V, this means that a slightly smaller lattice, a slightly smaller cylinder contains no point of the new lattice. And this is an open condition. And so the trajectory under the diagonal flow must cross this open condition infinitely many times. Mm-hmm. And so this explains that for lattices, it is almost every lattice, the constant is, as we just said before. And there is a second step because you must go to an almost everywhere in the space of lattices for an almost everywhere in the space of complex number.
Mm-hmm. Yeah.
And then you have something about the expanding direction of the diagonal flow, which you can use. And it gives you.
I see. So the condition is that the diagonal orbit of the lattice must stay away from some subset of the space of lattices. Is that? Is that what you're saying?
Yes. Yes. For almost yes. There are some subset. Yes, it can be formulated like that. Yes.
No, he's asking what are the lattices or the Z for which the constant is not the one you computed, and these lattices are the ones that avoid this this point omega and the corresponding lattice UV.
Avoid the point or avoid the set of points?
In a small neighborhood. Actually,
is it just a point or a set of lattices with this property?
It must be a set.
No. You can construct a lattice that avoids the open set near this point W1, W2.
Yes.
That avoids the neighborhood. And for this lattice that you've constructed, you will have another constant, not the supremum.
Mm-hmm. Yes.
Yes.
But of course, it has zero measure. That's what he answered, actually, to show that almost every Z will have the.
Yes.
But this is just because, right, the geodesic flow brings almost every orbit to this open set, but not all of them, usual.
Yes,
But
yes.
I think, Nicolas, that what Dimitri is asking is, can you like characterize the Z's or that do not go? Can you characterize some vector Z for which the constant is not?
This is a related question. For example, in the real case, Devertworth and Schmidt proved that it happens if and only if the number is badly approximable.
Yes, yes.
Right, but this is
Yes.
not this is not the case for complex numbers.
I don't know. I don't
Probably.
know. I have not think of. It's no, I don't.
Okay, so Felipe, there was a
There's
question
a,
in chat. Maybe you can.
yes, I'll communicate the question from Fastan. The question is, can the Voronoi algorithm be applied to determine the successive minima of the product that appears in Littlewood's conjecture with two fixed real numbers?
May you repeat the question? Voronoi.
Can you use the Voronoi algorithm to determine the successive minima? So from the product in Littlewood's conjecture. So there's this Littlewood conjecture.
Yeah. This can be an idea to go into the direction of Littlewood conjecture to look at all the minimal point. But it is not easy. I have tried to look at it, but
Which Littlewood conjecture?
I'm not alone. Just look at the studies, the property of minimal point. For instance, if you take a lattice in R3, in fact, you take a lattice, a real lattice in R3, and you can try to look at all the minimal point of this lattice. And the volume of the set defined by all these minimal vectors will be related to Littlewood conjecture.
Okay.
But I don't know. There are some old work, Russian work about this kind of thing. Old and not old.
Fastan asks a follow-up question. Is it easier with the p-adic Littlewood conjecture?
I don't know.
Yeah, it's a good question. Maybe.
But wait, sorry, I still don't understand. Littlewood conjecture, you mean you have two real numbers, alpha and beta. You look at Q alpha, Q beta, or what is it?
Yes.
So, but this is expected that the minimum must be 0, right? So what does it mean, successive minima of the product appearing in the Littlewood?
Yes, you can, if you take the lattice defined as lambda z, so the lattice defined by, how can I say, Q alpha minus P1, Q beta minus P2, and Q. This triple of points, you can look at as this triple, and then you can look at the minimal point. And if you look for each of these minimal points, it defines some parallelepiped, three-dimensional parallelepiped, and the volume of this three-dimensional parallelepiped is just the product you have in the Littlewood conjecture.
Okay.
Yes.
Just one question, like you gave this proof using the first theorem on the primality of two consecutive minimum vectors, and then you at the end you showed some induction on W1 and W2. So could this induction on W1, W2, this recursive relation, could it be also a proof, another proof?
Sorry, I don't understand exactly. The last theorem?
Yeah, here. When you write this equation one, can it give an alternative proof to the optimal condition, to this constancy?
I don't think. I think it is. You see, it is somewhat independent, this theorem, because here we define a map. We can say a map which associates W prime to W, and but we have not explained what is the domain of definition of this map in the theorem. And the domain of definition of this map is given by the theorem I gave before.
Okay. But iterating this map gives, nevertheless, at the end you can see the maximum, or no?
With this map?
Yes.
The maximum for Dirichlet constant?
Yes.
Yes. You can compute it with it. You just take one point, you iterate it, and you compute the function with 1 point. You can approach the maximum.
Okay, but you need a domain of definition on which you can, to ensure you get really the maximum. Okay. Thank you.
Other comments or questions?
Yeah, one more question. Your constant is like for Dirichlet improvable, like for all kind of. So my question is, can you say that is it known what the best constant would be when you only want like infinitely many approximations? Then the constant should change maybe, right? Well, maybe.
Maybe it depends. If you just want that there are infinitely many approximations, you think of Hurwitz result, for instance, in the
something like this. Yes.
Yes, it is known in the complex case that the constant in the real case it is 1 over square root of 5, the Hurwitz constant, and in the complex case it is 1 over square root of 3. So you have infinitely many pair PQ such that QZ minus P is smaller than 1 over square root of 3 times modulus of Q. I don't know if it is your question, but
yes, that's exactly what I asked. Yeah, thank you.
And are the numbers that are badly approximable with respect to that definition the same as the ones that are improvable in the uniform sense?
I don't know. I don't know this. In the real case, but it holds in the real case, but in the complex case, I don't know.
Yeah, this was exactly my question. So,
yeah.
I mean,
yes.
I mean, my conjecture is that the answer is no. But it would be nice to have an example of the complement.
Mm-hmm.
So the proof for Hurwitz constant is similar to these computations you do and these considerations, or?
Hurwitz constants, no, it's the proof. I don't know the proof. In fact, it was proved at least 2 times, once by Ford. And I think there is the fourth circle in the, but I don't know the proof.
But it's some kind of continued fraction algorithm, I suppose, should be involved, right?
I think there is also a proof by Hurwitz continued fraction algorithm, which is possible, but not the same.
Mm-hmm.
I don't know.
You could do it with your technique?
I have not think about it. I don't know.
Interesting.
Well, are there more comments or questions?
Okay, maybe I can stop the recording for now, and then we can decide to hang on a little longer. So let's thank Nicolas anyway one more time. It was a great talk, and we see you guys every Monday for a while.